Hi everybody, welcome to my 14th torsional bar video. In this video I'm going to be developing the equations necessary to describe a torsional bar that's being used to transmit power. If you want to see an example of this particular situation and use of torsional bars, check out my next video. If you want to know something else about torsional bars, feel free to check out any of my other torsional bar videos. So to get a mathematical explanation of, a power being transmitted by a torsional bar, we're going to start with a very basic situation. So you can imagine a fixed point and a bar extending out from that fixed point a certain distance. We're going to give it a distance r, alright, for the radius, and it's being pulled with a force that's perpendicular, F. Alright, pretty straightforward situation. Pull on this, it's just going to spin around in a circle. So before you applied that force, it was here. After you applied that force, it's moved, it's gone to here. So this length, of course, is still r, but it's moved through some angle. We'll give it the Greek letter C, okay, and then you spell it like this. And it's moved through some distance here, alright. So radial distance, d, and we can describe the distance because we know the angle C is equal to d by r, or you can say simply d is equal to c r. Alright, so we're slowly working toward developing the power developed by something, so keep that in mind as we go through here. Now the torque by this is pretty straightforward. Alright, we can say the torque is just that force times that distance. In this case, it's the radius. Force times distance. Force times the distance it acts through, or the lever arm. Alright, now, the work done, I'll call that WD. We know in general that's force times a distance. Okay, so in our case, it's going to be this force, and it's moved through a certain distance. So the distance we know is CR, so let's replace that. The work done is equal to force RC. But hey, check it out. FR, force times the distance, is also equal to T, so we can say the work done is equal to the torque times the angle it's moved through. Alright, now to find the power. Well, power, P, is the rate at which work is being done. Alright, so work done per second. And when I say the rate of work being done, that's basically the derivative of this with respect to time. Now we're going to assume that T, or the torque, is not changing with time, so that force is always being applied at that distance. The distance is staying the same, so that remains constant. But this angle is changing. So we can describe the angle is changing by this if we take the derivative with respect to time. And hey, we know, switch back to my black pen, the change in angle per time, that's just angular velocity, and we give that the Greek letter omega. So we can say the power is equal to torque times omega, and this is the key equation. And so far in torsional bars, we've been dealing a lot with torque. And now we have these two extra variables added. So the questions you'll see will often be like, you have a shaft, it's spinning, it might be hollow, it might not be hollow. Alright, it's spinning at a certain rate. They might give you that rate in RPMs or cycles per second or frequency or something. They might give you power in some sort of other units like horsepower or foot-pounds or something. And then it's up to you to calculate the minimum diameter of the shaft required so it doesn't break with a certain shear stress. So basically now it's just a bit of algebraic manipulation and dealing with units of things to make sure you can find what you need. So some common things that you'll be given is horsepower. Alright, so power is given in horsepower. You don't just give, this is measured in watts. We can see that because T is Newton meters, and W is just cycles per second, rads per second. rads per second. Radians, that doesn't actually have a unit, so really it's just Newton meters per second. That's of course equal to a watt. Named after James Watt, the guy who made the steam engine. So basically, what you might see in textbooks is they'll take this radians per second and convert it to like an equation that gives you horsepower. I like to keep this equation simple, find out what omega is in terms of if you're given horsepower, what is this? Develop that on the side and then plug it back in terms of omega. So let's just run through a few common units you'll be given. So 1 horsepower is 746 watts. Alright, so in reality a horse can't produce 746 watts, that's actually quite a bit. But in the time when they were developing this sort of notation, a horse could do like 200 or 300 watts. And they were really developing things to do with biology and horse breeding. So they figured in a certain amount of time a horse can deliver 746 watts. Alright, maybe 100 years from when they thought a horse would be able to do this much. When they were developing it in the 1800s. But a horse still can't do that much, but we still call it 1 horsepower. Okay? And this omega, that's the key. This has to do with power, of course. So omega here, it's measured in radians per second. So we need to make this equivalent to if we're given RPM. So RPM is really just, rounds per minute. So we're going to make this to radians per second. So we're going to times it by minutes over seconds. Well, there's 60 seconds in 1 minute. Now we're at rounds per second. I'm going to times that further by 2 pi radian per 1 round. Alright, and there you have it. Our rounds cancel off. We're left with radians per second with some sort of factor. So rounds per minute, we usually call that N. So it's going to be times 2 pi by 60 equals W. And then you could just take this whole thing and plug it into here. Alright, another thing they might give you lots is frequency. Alright, so the number of cycles per second. Okay, so cycles per second. And we need to somehow get it to radians per second. So we already have per second, so we need to change cycles to radians. Well, there's 2 pi radians in 1 cycle, because a cycle just means starting at some point and going all the way around to that point again. And there's 2 pi radians in that. So cycles per second, frequency, usually F, times 2 pi equals to W, or omega. And my physics teacher, I would always correct him and say W, but it's actually he's correcting me saying omega. Anyway, so these are some 2 common, ways you can transfer one type of units into another unit. Like I said, I like to do it on the side just to make sure I'm understanding what's going on rather than just plugging this into here and using the formula. Alright, so that brings me to the end of my little derivation here. And we'll see you in the next video. Let's do a practical example.